Let me share screen. Can you see it?
Yeah.
Great. All right, so I'm going to give a quick overview of CertiKOS and then talk a little bit about limitations, lessons learned, and the future plan. So I think the CertiKOS project is a little bit different from the general C code verification. So we are mostly focusing on verifying OS kernel, hypervisor, security monitor. And so in that context, we are interested in verifying system modules written in C and written in assembly and linking them together. So when I talk about the problem definition, we are really interested in deliver what we call system binary, that you have a proof showing the binary implements its specification, but also running over a hardware machine model with potentially device and interrupts. So it's not the just usual abstract machine written in PL context. Instead, it's a vastly more complex hardware machine model, as you commonly see in the typical system. So a big part of this challenge is on what the specification should be like, what the machine model should be like, because it kind of dominates the complexity of the challenges. And on top of this, we are not just interested in verify safety and partial correctness properties, because you are going to work over several thousands or tens of thousands of lines of code. You don't want this verification be limited to prove just one type of safety property. There's lots of other property you also have to prove. If you deliver a certified hypervisor, you only say it's safe, but it's not secure, it does not provide isolation, it's kind of not that interesting. So you want to, at the very beginning, think about, in the end, after you have done all the verification, do you also prove these other properties like security properties, resource usage property? You clearly don't want to have a Stack Overflow, right? Real-time property, race freedom, right? Atomicity, and the kinds of liveness properties. So you can't just say, oh, wait, let's first work on safety, then slowly migrate to these more advanced properties. You need to have the end in mind when you plan things around. And on top of this, you want to cut down the cost of verification. So the conventional approach would say, okay, if you want to prove safety, I develop one program logic and I try this and verify this kernel support property one. And if I have another property like a security property or isolation property, information flow property, I develop another program logic to verify this OS kernel spec too. And so that kind of things is not what we want, because I don't want to go through my kernel C and assembly multiple times for each properties. So the idea has always been in our group is that I want to do the verification of the code once, and then try to derive all these different properties you know about, like security, like liveness from the spec. So to do that, you have to really high quality functional spec, which, borrowing the word, we are using the term deep functional spec to mean something that captures pretty much everything you want others see in the kernel binary and the hardware machine model. So that's the philosophy of CertiKOS. And so what is the deep functional spec? Well, you might see actually OS kernel or hypervisor contain many system calls. So they will have many APIs. So you will split this spec into many different modules, components, and you hopefully there will be a corresponding OS kernel binary split into the different components. And they are often, some of them are written in C. So you kind of have to split the verification, right, in a modular way. But again, this horizontal flattening, decomposition itself is neither realistic nor enough. Because in practice, the functional specification for OS kernel is hierarchical. Because at a different level, you have different abstractions. When you have when the machine boots, you only have the bare machine. And then when you build up the virtual memory, you kind of have the virtual memory mechanism actually get to work, and then you add the threading, and so on. So the envision is that the specification will be hierarchical. Your code has to be organized the hierarchical way, and the C code, right, has to be compiled into the proper assembly code, which will implement the kind of the hierarchical specification. So if you zoom into these hierarchical spec or hierarchical modules, you would start to wonder what the spec would look like. So clearly, these specifications should be very rich, ideally specify the function specifications. But what's the definition of rich? That's a key question that we always struggle with. So, so rich is a kind of an ambiguous word. So if I want to build one rich spec, I have another rich spec. And if verification needs to revisit the whole code, then it's not really what we mean by deep spec. So we don't want to, when you want to establish another property on the same code base, reduce the verification. So instead, we want some notion of a deep spec, or you can call it a fully abstract spec. So the idea is, if you are implementing a module M of an underlay L1 and there's a layer interface L2, you want them to be almost equivalent or simulate each other. So in the context of CertiKOS, or in the past work, we define a notion of a deep spec, saying that if the interface L2 behaves same like M over the underlay L1, if under any valid program context P over L2, however this M gets used, the semantics of running P with this implementation M is the same as running this P with this overlay L2. So they are observationally equivalent. So that's our notion of a deep spec. And if you can do that, then you can truly, when you are verifying every module, you don't actually need the underlying code because the spec already said everything. So we can basically do the incremental verification, and we can derive a desirable property from these, specification alone. And so the CertiKOS approach in general was really try to develop a language-based formalization of this notion of a certified abstraction layer with deep spec. So we developed the formal layer calculus, a language called C-Lite-X, which is a C-like language extended with this abstraction layer interface. We have an assembly language, same thing, CompCert extension that compiles C-Lite-X to assembly code. And then we have built multiple OS kernel like CertiKOS, initial sequential version, later concurrent version, and some with device driver support, some with real-time guarantee, some with actual security proofs, spatial and temporal oscillations. So I'm going to skip these because it just shows that within the COG, how these layer spec are implemented. It's built on top of CompCert, and the concurrent version CCA, which actually start with per core. So take the abstraction layer infrastructure, first build every core abstraction layer or every core, and then build a thread library, per thread layer. And we have the multi-threaded linking, multi-core linking, try to link all these things together. So CCA has been used to verify CertiKOS. So in recent years, it has also been used to verify, for example, the SE KVM, the Linux KVM hypervisor, done by my former student Rong Hui and his Columbia group. And this verification was extended to ARM relaxed memory hardware. And they actually also recently used to verify the ARM CCA confidential computer architecture firmware. So if you look at their artifacts, they are pretty much following the same CCA infrastructure and using multiple layers, and they also verify security properties. So talk about the limitation, right? I give you a summary what the project is about. What are the major limitations we have discovered in the last few years? The first is we are not happy with our definition of what we mean by deep. And the main reason is because this notion of a valid program context is kind of a closed notion. we are kind of restricted by the underlying language. If we use assembly as the language, then we are basically talking about all valid assembly program context. So ideally, I want this to be open notion, open context. What does that mean? Well, because we don't know what the machine model will look like. When we are using these different OS component modules, the underlying hardware architecture is evolving, right? And it might involve multiple language features. So, so we want to have a notion of a component that sits on its own and talk about its interaction with its environment. And ideally, this program context is can be constructed as we go. As we accumulate more and more components, we accumulate more interesting program context. So, along this line, we have been exploring extensively over, ideas of using game semantics to model these different OS components, basically. The second limitation is related to CompCert and also our CompCert X compiler, which was developed, around 2015. So we have done a lot of work along this line. First, of course, everybody knows CompCert is not a compositional. Does not support really compiling what we call open modules, and the CompCert X mechanism to ad hoc. So we have a new work called the CompCert All, which is kind of a extending CompCert with support for some general notion of a compositional semantics, so that you don't have to specialize CompCert with these abstraction layer. Instead, the compositional semantics automatically support this notion of external function call and link them together. And the other one related to CompCert, the CompCert really does not support finite stack, consecutive stack, and multi-threaded stack. So we have done much work recently on how to support stack-aware CompCert and how to support multi-threaded stack-aware CompCert so that the CompCert can support multiple stack at runtime. The third one is related to generate machine code. Again, we are trying to add a verified assembler behind the CompCert. So these different versions of CompCert will be now capable of generating verified ELF binaries. The third limitation is related to concurrency model. And as you probably can expect it, there's a lots of limitation of current CCAR. It does not support a weak memory model, even though the Columbia group has done a little bit work along this line, try to extend the CCAR to deal a little bit with weak memory models. The second one is CCAR threading model is rather restrictive. Right now, we basically only talk about the multi-core, and then on top of them, we build multiple threads under each core. Ideally, we want to support all kinds of user level, kernel level thread library, basically supported under our kernel and give different combination of a user level, kernel level thread. So that's something CCAR currently does not support. The third one is the CCAR support for blocking concurrency is actually quite poor. We managed to verify yield, sleep, block primitive, but they are not really very clean. So these are primitives like it's easy to verify ticket lock because it's a kind of a spinning lock, right? But if you try to verify in queuing lock, like those when the lock is not available, you put yourself to sleep, you have to model these blocking operation cleanly. So it's a kind of a challenge that most concurrent verification mechanisms do not address. And this other one is another limitation. The CCAR is very biased towards linearizable atomic objects. We kind of try to make every layer only expose the atomic primitives. And occasionally we see some that's not atomic, then things basically gets very complex. Again, and once the other one is the CCAR is still based on closed context. When we say CCAR is concurrent verification, when we say it's linearizable atomic, it's a contextual refinement with respect to a rather limited, global program context. So again, you could see that the kind of emphasis of contextual refinement and game semantics is really preparing us for developing a more general model for reasoning about concurrency. So that's the kind of work we are working on. What lessons we learned? I guess out of all these work we have done, the first is we really need to worry about the program context, because it decides in the future how much your module can be used. It's not just about verifying a single module against your spec and then everything's done. Especially when you are talking about the concurrency, especially when you are, when you want to use these modules in a large scale system. The second is looking for a general shared memory concurrency model that is compositional. That's kind of a challenge, right? So we still don't have that. You build a concurrent module, you want to compose with others, and how these things should be composed. I think much research is still needed to develop a truly compositional concurrency models. So there's lots of challenges along this line. In fact, you could imagine, right? It wouldn't be called OS if you don't support these type of concurrency. So that's kind of, to me, it's a very high priority problems. The third lesson we learned is, in my career, we have done large scale verification multiple times, and it's always at the end we realize, oh, we only verified one property, and when I want to verify another property, suddenly, my early mechanism no longer work. So it will be useful sometimes, to begin with the end in mind. That is, what whole system property do you actually want to verify, and what kind of hardware machine model you will rely upon, and how do you actually, change things if the model evolve rapidly, given the current state of the art. So I think that we are happy with our current approach because it decouples the code verification from the verification of specific system properties. So future plan, I just put this together quickly last night. We are developing this compositional game semantics, general concurrent components. We are in the middle of developing this new CCAR based on this new game model. All the CompCert work we have done in the past few years are integrated into a single version called the nominal CompCert that can compile these concurrent layers into ELF binary layers. And we are continue to extend our deep C language. I didn't mention much in this talk, but it's essentially try to write the spec, synthesize the corresponding C components and supporting the composition. And then we are trying to apply deep C and CCAR to build a more powerful version of CertiKOS and some other enclave-based OS work that we have been doing recently, basically. That's it.
It's great. Thank you very much. Quick questions or comments with respect to Zhong stuff? And then after that, I want to move on to some more general chat.
I have a question. So a lot of what we've been talking about is kind of like verify a little library, maybe verify this chunk of C code. What would need to happen? What sorts of problems would we need to have in a benchmark suite in order to evaluate the sorts of problems that you're working on to do a head-to-head comparison sort of thing?
I think again, when you build a benchmark, it will be important to decide what the audience or what the purpose is, right? So user level program could be very different from the, OS kernel hypervisor programs. I mean, examples like a virtual memory manager could potentially be made very small and could potentially become benchmark. Like the thing we talked a little bit about, virtual memory versus physical memory, how they get linked together. That kind of interesting because surprisingly, in some cases, like the previous talk, right? CertiKOS verification we didn't rely on separation logic that much either. And the reason is because the CompCert memory model already provide block-based memory model, and the blocks are already separated from each other. And we kind of lift them into the abstract state, so that by the time you get to abstract state level, they are already separated. And so the verification done at the, when we do the actual system verification, the abstract state is kind of already more like a functional data structure and offer better support. So what I'm trying to say is, it really depends on what you are evaluating, right? If you are evaluating just for general C benchmark, most likely at user level, then probably some of these things we talk about here may not totally overlap, because we are focusing on the concurrency model, we are focusing on the how to put the different pieces together. On the other hand, I would be super happy if the benchmark suite also emphasize modularity and the concurrency rather than just the individual C modules.
I agree. Okay.
Yeah. Okay.